right now. Creation Ministries International and Bible Discovery TV Network present the Creation Super Conference of 2011. We're blowing your mind with biblical truth in a stunning display of discoveries in science. Join us now as we go live from Muskoka Bible Camp into the Super Conference with Bible Discovery TV and Creation Ministries International.
Good morning, good afternoon, good evening, wherever you are. Rod Hember here. We are live at Muskoka Bible Conference. I'll get that right before this whole thing is over. You've been watching a little bit of the pre-show, which is basically worship services. And we are going this morning to, I know this is the first thing we do in the morning, nuclear physics. I know, that's like killing you, you know. What's the first thing you do in the morning? Breakfast and nuclear physics, that's right. But actually, Dr. Jim Mason is going to be telling us about a young Earth. And also, a little bit later on this morning, Dr. John Samford is going to be talking about evidence that evolution actually hurts science. Now, that's fascinating. Now, later today, my good friend, Gary Bates, is going to tell us about the alien intrusion. The alien intrusion. I think I saw a UFO last night. What's going on around here? Well, Gary Bates has the idea on that. What's going on with that now? Not to make light of it, because actually there's a strong bit of evidence, both in the Bible and out, that alien invasion and intrusion is actually demonic forces. Whoa, what are you talking about, Rod? I love Star Trek. You're saying Spock was a demon? Well, hey, stay there and don't jump to conclusions. Let's listen tonight to Gary Bates. So you want to stay around for that. Right now, we're getting ready to go inside for Dr. Jim Mason, who is his expertise really is physics. And this is really interesting. And so today, as we focus, Richard is going to set him up and pay attention. This is a good one. I'll be back between the breaks to talk to you more about what's going on today. Let's go inside now and introduce our first session.
All right. Well, how did you enjoy the sessions yesterday? Pretty good? How are you enjoying the food? We got lifted hands for that one. We'll have an amen for this one. How are you enjoying the facilities? Isn't that great? It's a wonderful place to learn and to relax. Well, we have another full day of sessions coming up, and a bit of that brain melt happening yet that we were talking about, or drinking from the fire hose, the other analogy there. A few announcements first. CMI has an Air Miles program. We have, you've heard of Air Miles? You go around and you swipe your card at various retailers and you get points, and you can collect things, you can get free flights after you have enough points and so on. Well, our speakers fly across the country to speak in churches. And you can get an Air Miles card from CMI, from over at the hub here, get a little card that you can swipe when you purchase things at retailers all across Canada, and the Air Miles that you collect with the CMI card will go to the CMI account. And then our event planners can use those miles to get free flights for our speakers. It's a way that you can support the ministry without having to budget for it. And it helps us out tremendously. And you can also, you can get Air Miles MasterCards and American Express. You can call up the customer service folks and tell them you'd like to credit your Air Miles that you're getting on your credit cards to the CMI Air Miles account. And so you just get our account number, and all of the Air Miles that you get on your credit card, you can just have those go to CMI's account. And again, we'll use those to get free flights for our speakers. So it's a way that you can support the ministry. And you can talk to the folks over at the table there to get a card, or to talk more about the credit card system, how that works with getting Air Miles to CMI. It's a great support for the ministry. Again, off-site guests, if there's anyone here who's just here for the day, or just coming every day and you're not staying here, or you're not paying for the meals, if you want to use the facilities down at the lake and so on, there is an amenities fee, a small amenities fee, and you can pay for that over at registration here, a couple buildings over. The numbers for yesterday, what did we have for yesterday as far as the live broadcast is going? It's ranging between 18 and 22,000 people, so around 20,000 people are, yeah. all around the world are tuning in. There's an additional about 5,000 to 6,000 people watching on iPhone and mobile devices. Hopefully not while they're driving. Don't watch while you're driving, although many people do. Some people do. Some people who should know better do. But we won't mention any names, will we, Rod? But some of you may have noticed that some of the resources have disappeared from the tables. Don't worry. There's a replenishing coming tomorrow. So, for example, Stones and Bones, that disappeared yesterday after I mentioned that, and I think someone else mentioned that. They're gone. We don't have any more. We'll get more coming up. If we get toward the end of the week and we've completely exhausted our supply, we can ship that to you from our warehouse in Kitchener, from our office in Kitchener, and you can just fill in a little order form, and we'll ship that to you with no shipping charge. It's as if you picked it up here at the conference. We apologize if we do run out of anything. We do hope to keep those stocks up. All right, our first speaker this morning is Dr. Jim Mason. Jim has a Bachelor of Science in Engineering Physics from Queen's University in Kingston, Ontario, Canada, and a Ph.D. in Experimental Nuclear Physics. I love saying that. It's Experimental Nuclear Physics from McMaster University in Hamilton, Ontario. Jim grew up attending church regularly in a mainline Protestant denomination, reaching high school graduation without ever hearing the message of salvation, and left the church and the faith when he took Geology 101 in first-year engineering. Although he and his family resumed church attendance in another mainline Protestant denomination, because he and his wife thought it would be good for their two young girls. It wasn't until almost his 40th birthday that he heard the message of salvation when attending an evangelical church in response to the invitation of a friend and neighbor who subsequently accepted Christ. However, Jim was initially what we might call a bipolar Christian, believing in salvation provided by Jesus, but also believing in the evolutionary account of origins, the Big Bang, etc. It wasn't until he attended a weekend seminar conducted by young Earth creation scientists where he saw that Scripture and science were completely coherent, and they fit together. Since that time, largely as a result of information available from CMI, he has become increasingly amazed at how the truth of Scripture is confirmed in every area of science, and become increasingly concerned about how evolution is used as a means to avoid confronting the claims of Jesus. Dr. Mason's hobbies include skiing, downhill and cross-country, gardening, landscaping, renovations, and spending time with his two grandchildren. Please welcome with me Dr. Jim Mason. Come on up, Jim. All right. All the best.
Okay, yes, the technology is working. Well, good morning, everyone. And I would like to pick up on something Richard said about the air miles. I'd really encourage you to participate in that program. I'm getting tired of hanging onto the wing of the airplane. Well, isn't this great? Here we are, a beautiful sunny day in beautiful Muskoka, at 9 o'clock in the morning, in a talk on nuclear physics. I haven't done that since I was in university. Of course, back then there was somebody else up here, and I was out there, hoping that the guy up here wasn't going to be too boring. Just like you probably are this morning. Well, so am I. Anyway, thank you for coming. Thank you especially to those of you who are here who aren't part of my immediate family. And to those of you who are watching from the West Coast live on the internet at 6 a.m. in the morning, God bless you. Okay, we're going to talk about nuclear physics in the age of the Earth. And yes, there is evidence to suggest the Earth is young. So, why are we having a talk on nuclear physics at a conference on creation? Well, research tells us that 67% of young people leave the church at age 18 and never return. Now, that's pretty serious, right? One thing, if this keeps up, the church is going to become extinct pretty quickly. But the really significant thing is these people are potentially giving up their opportunity for salvation. Now, why do they leave? Well, Calvin Smith, in a recent edition of Creation magazine, wrote an article in which he quoted a campus evangelist as saying, "My time on college campuses and talking to high schoolers, the number one answer that I get for there not being a God, so then I don't have to believe in the gospel, is evolution." So maybe there's a connection. That view, that evolution is potentially the root cause, is confirmed by these data, which is the result of a 3-country survey, or opinion poll, conducted by a company called Vision Critical on the beliefs that people hold on our origins. The 3 countries were Canada, the US, and the UK, and these are the Canadian results. And you can see, although the US and UK results are not much different. But you can see 68% of the people in the 18 to 34-year-old category believe in evolution, the same number that leave the church. Now, as an aside, these data also have some other interesting nuggets. For example, these 2 numbers tell us that women are wiser than men. And these 3 numbers tell us that older people are wiser than younger people. And if you put those 2 together, what do you get? You get that older women are the wisest. But then I already know this because my wife's just a bit older than I am. Now, long ages, deep time, is the bedrock foundation for evolution. Charles Darwin latched on to the idea of deep geological time that was put forward by Charles Lyell as the thing he needed to make his slow and gradual evolution possible. Evolutionists tell us that man evolved from some ape-like ancestor over about 6 million years. But that's just a small fraction of the time they tell us it's been since life was formed 3.5 billion years ago. And of course, the Earth would have had to have been around for some time before that. So, what does nuclear physics have to do with the age of the Earth? Well, everything, then nothing. That's the sort of the uncertainty principle. Let's deal with the nothing part first, because it's usually easier to deal with nothing than everything. We've heard several times already that the Bible is the history book of the universe. How much history is in the Bible? Well, it starts at the very beginning, in the beginning. And the historical part of it runs through until just after the death and resurrection of Jesus. And if you use the genealogies in the Bible, you can figure out that there's about 2,000 years from creation to Abraham. And if you use other information in the Bible and from other historical sources, you can figure out that there's about 2,000 years between Abraham and Jesus. And then, of course, our calendar tells us that there's been about 2,000 years since Christ was born. So, 6,000 years. We've figured out the age of the Earth is 6,000 years. The Bible tells us that. And it doesn't even mention nuclear physics. Now, Dr. Faulkner last night was lamenting the fact that geologists get several chapters in the Bible, and he has to deal with only 3 words. Well, nuclear physicists don't even get 1 word. Not even a jot or a tittle. Now, some people don't agree that the Bible is the history of the universe. So where would they look to find out how old the Earth is? Well, it used to be you'd look at an encyclopedia. But these days, you Google it. So if you Google the age of the Earth, what do you get? You get a list like this. And the very first entry on the list is a link to Wikipedia. Now, I don't necessarily recommend Wikipedia as a source of reliable, trustworthy information, but I think a lot of people go there to find out stuff. So let's go see what Wikipedia has to say about the age of the Earth. It says the age of the Earth is 4.54 billion years. Notice, it says is. Not we think it is, it might be, but it is. No ifs, ands, or buts. Doesn't brook any discussion. It is 4.54 billion years. Then it goes on. That means 4.54 times 10 to the 9th, plus or minus 1%. Wow, that's really accurate. They must really know what they're talking about, right? Well, actually, it's not accuracy at all. It's precision. And to understand the difference, consider the micrometer, which was developed to make very accurate and precise measurements of machine parts. Now, the precision comes from a special scale on the barrel called a vernier, and it allows you to make very, very small increments of measurement of the width of the machine part. But the accuracy comes from the shaft. And if you were to cut off a portion of the shaft, it wouldn't affect the operation of the vernier, so you could still get these very precise measurements. But because you're missing part of the shaft, they would be wrong. So you would be precisely wrong. Now, it's important to remember that for later on. So Wikipedia goes on. This age is based on evidence from radiometric dating. So we're going to have to talk about radiometric dating, and that's the nuclear physics stuff. Now, one would think they'd use radiometric dating on Earth rocks to find out how old the Earth is, right? But they don't. They date meteorite material. And that's because of their assumption that the Earth and meteors were formed at about the same time out of the same material. So they figure it's better to use the meteorite material than the Earth rocks. So how does radiometric dating work? Well, there are three kinds of radioactivity: alpha, beta, and gamma. These were the names that the scientists gave to them when they first discovered them, when they didn't know anything about them. So I think it was kind of an attempt at erudition, if you like, by association. If they used Greek letters, everybody thought that was really cool. Eventually, they found out that alpha particles were helium nuclei. That is, they consist of 2 neutrons and 2 protons. They found out that beta particles were mostly electrons, but sometimes were positrons, which are really electrons with a positive charge rather than a negative charge. And gamma rays were radiation like X-rays. So in alpha decay, the nucleus gets all excited, and it spits out an alpha particle and feels better. In beta decay, a neutron changes to a proton, and when it emits an electron, has this electron left over, and electrons aren't allowed in the nucleus because it's a very exclusive community, so it's ejected from the nucleus and travels on its way. And in gamma decay, the excited nucleus gets less excited by emitting a burst of radiation. Kind of like, we do when we hammer our thumb or something like that. Now, some of you may have come across or be familiar with the periodic table, which was an attempt to organize all of the elements based on their chemical properties. There's a similar arrangement to organize the elements based on their nuclear properties. And this is called the chart of the nuclides. And it's a plot of all of the elements using the number of protons and the number of neutrons in the nucleus as the axes for the graph. Now, the number of protons determines what element it is, and the number of neutrons determines what isotope it is. And any particular isotope for a particular element is called a nuclide. That's why it's called the chart of the nuclides. And the little black line that runs up the middle, squiggly line, is where all the stable elements are. And the heaviest stable element is lead. All of the colored bits undergo some kind of radioactive decay. The yellow ones undergo alpha decay. The pink ones, if I can use that, undergo beta decay, beta minus decay. They emit electrons. And bluish ones emit positrons. And the few green ones, way up at the top, they undergo fission. Now, if we explode this up and look at it more closely, you see this kind of thing. See number of protons up the left and number of neutrons across the bottom. And if you start out with an element with Z protons and N neutrons and it undergoes decay, it actually changes the element. Right? So if it undergoes beta minus decay, it increases one of the neutrons changes to a proton, so it increases the number of protons and decreases the number of neutrons. And conversely, it goes the other way for beta plus decay, and when it emits an alpha particle, it makes a big change. It goes way down. For example, if the numbers there are 17, 18, 19, and 20, then the actual elements are chlorine, argon, potassium, and calcium. Now, gamma decay doesn't actually change the element, but we're not going to talk much about gamma decay anyway. So how does the process go on? Well, you start with the radioactive element, and it decays to a stable element. Now, the radioactive element is generally referred to as the parent, and the stable element is generally referred to as the daughter. Having had 2 daughters, I find this association, shall we say, interesting. And the decay can be either alpha decay or beta decay, and it occurs over a time period, special time period that's known as the half-life. Very important. The half-life is the length of time it takes 1/2 of the parent element to change into the daughter element. Okay, so if you start with 4 lumps of parent, after 1 half-life, 2 of those have changed to daughter, and you're left with only 2 lumps of parent. After the next half-life, 1 of those remaining 2 lumps of parent changes to daughter, and you're left with 1 element of parent, but you have 3 elements of daughter. So if you put this on a graph, it looks like this. You start out with all parent, no daughter. After 1 half-life, half the parent's gone, been replaced by daughter, so they're the same amount of each. And then after the next half-life, half of that parent has transformed, so you now have 1/4 of the parent that you started with, but you have much more of the daughter, and so on. It goes on like that. And if you plot, or if you then look at compute the ratio of the amount of daughter that you have to the amount of parent that you have after each half-life, you get these kinds of numbers. Okay? Now, if you plot those numbers on a graph against time in number of half-lives, you get a graph that looks like this. Now, we can use this graph to determine how old something is. If we can measure the ratio of the daughter to the parent now, in this sample of whatever it is, then we can project that across to where it meets the curve, and then look down and find out how many half-lives have gone on since this decay supposedly started. And if we know the half-life, and they're all generally well known, we can calculate how many years or minutes or seconds or whatever that has been. So let's look at how this works in real life. These are the typical radioactive decay chains that are used for radiometric dating. There are 4, there are some others, but these are the 4 most prominent ones that are used for measuring igneous or metamorphic rocks, and I'll talk a little bit more about that in a minute. So there's uranium to lead, potassium to argon, rubidium to strontium, and then over there on the right, there's one technique that's used for radio dating organic material, and that's the well-known carbon-14 process. So let's look at this one in particular, which is frequently used because it's easy. It's easy to measure, right? Looking at this expanded view of the chart of the nuclides, we have the parent, which is the radioactive potassium-40, and it decays actually in both directions, to calcium and to argon. But it's the decay to argon that is important for radiometrically dating rocks. It has a half-life of 1.25 billion years. And the reason it's used is that the theory is that when the rock is molten, really hot, all of the argon, which is a gas, is boiled out of the rock. So at the time when the rock solidifies, there's assumed to be no argon in the rock, so any argon you see in the rock, when you measure it after it's become solid, is a result of the potassium decaying to argon. Well, how does this work? There's this volcano in New Zealand with a pretty much unpronounceable name, for me anyway, and they've had, it has erupted 3 times in the recent past. Once in 1949, that's the oldest one. So they took 2 samples of rock from that eruption and had them radiometrically dated using the potassium-argon technique. And these are the results they got. Well, I guess one is less than 270,000 years. And I guess you could say, 50 years is certainly less than 270,000, but there are a lot of other ages that are less than 270,000 too. And the next one is interesting. It says the rock is 1 million years old. And here's where this precision comes in. They think that's a pretty precise measurement, because they say it's only plus or minus 200,000 years. Okay, so they're saying that this measurement says this rock is somewhere between 800,000 and 1.2 million years old. Well, we know it's only 50 years old, so they're precisely wrong. Then the volcano also erupted in 1954, and they took 4 samples of this rock. Again, they got one that came in at less than 270,000, but one came in at 3.5 million. Again, very precise, plus or minus 200,000. And there was another eruption in 75, and they took 2 samples of that and got the same results that they got in 1949. or for the 1949 eruption. Now, if you plot these on a graph, they look like this, and you can see they're kind of all over the place. They not only don't agree with the real age, but they don't agree with each other. And this one comes in at 70,000 times the real age. Mount St. Helens provided another opportunity to test this technique with rocks whose age we know. And they used a couple of different approaches with the Mount St. Helens rock. So they used what is called a whole rock technique, where they take all of the minerals that are in the rock and they grind them all up together and they age the whole rock as a kind of conglomerate. They got 350,000 years old for a thing that was formed in 1984. Then they separated out each of the minerals and did a separate test on the individual minerals. Feldspar came in at just about the same age as the whole rock, which probably means the whole rock is predominantly made of feldspar, but some of the other ones were way off. This one came in at almost 1 million, this one came in at almost 2 million, and this one came in at almost 3 million for a rock that was formed in 1984. So why is this? Well, consider for a moment this graduated cylinder, which is a common piece of apparatus in high school chemistry labs. It's got 300 milliliters of liquid in it, and the liquid is dripping in at the rate of 50 milliliters an hour. So how long has this cylinder been filling? Well, the simple answer would be 6 hours. But that might not be the right answer, because what it doesn't take into account is that when you started, there was already 100 milliliters of liquid in the bottom of the cylinder. And then partway through, when there got to be about 200 milliliters, the lab assistant knocked it over and spilled a bunch of it. So he put it back up, and then he opened the spigot up to make up for it. So there are a lot of assumptions that go into the calculation about what's happened in the past that you can't know unless you were actually there and saw it all happen. And it's the same with radiometric dating. There are some assumptions. The calculation is pretty straightforward, but the assumptions are very important. And they consist of, what are the starting amounts? Do we have a known starting amount of the daughter and of the parent, particularly the daughter? Has anything been added to or taken from the parent, the amount of parent that's in the rock? Or has any of the daughter been taken out of the rock? Or maybe there's been some added from somewhere. Or indeed, has the rate changed with time? Now, to see what sort of impact these assumptions have, let's look at the starting amount. Here's the classic model decay chain. No daughter present at the start. And if you look at the different times here in terms of half-lives, 0 at the start, 1 half-life, 2 half-lives. You look at the daughter to parent ratio. You see there's 0 daughter to start with. They're both the same after 1 half-life, and there are 3 times as much daughter as parent after 2 half-lives. Then if you were to measure that ratio, you would find 0, 1, or 2. And in fact, that's precisely what you would expect given the actual ages. So in this case, where everything is as assumed, the measure value turns out to be exactly the same as the actual value. Now, what happens if you have some daughter present at the start? Here is the classic decay model. Here's the curve, just for reference, so that we can look up numbers and decide how old things are. Now suppose we have some daughter product that's present at the start, and it stays there. The same amount stays there all through the life of the rock. Now, if we measure the ratio of parent to daughter at these 3 different times, we get the following: 1, 3, and 7. And if we look up on our curve, we see that 1 corresponds to 1 half-life, 3 corresponds to 2 half-lives, and 7 corresponds to 3 half-lives. So those are the ages that we've measured. But in actual fact, the ages are 0, 1, and 2. And the presence of the daughter has messed up our measurements. And if you look at the ratio of these 2 things, you find out that that effect is most significant very early on, when you're at a very small fraction of the half-life, like right at 0. It's an infinite effect. Just off 0, very large effect. So when you're at a very small fraction of the half-life, this contamination, if you want to call it that, or this deviation from the assumption has a very big effect. And if you look at what 6,000 years is as a fraction of the half-lives that are typically used to do radiometric dating, it's really small. So a very tiny difference will make a very big difference in the estimated age. All right, so the potassium-argon thing doesn't work very well, and scientists recognized this and attributed it to argon that wasn't properly degassed out of the rock. So what to do about it? Well, they looked at another decay chain, this rubidium to strontium one, and rubidium-87 is the radioactive one. It decays to stable strontium-87, but strontium also has another stable isotope, strontium-86, that is non-radiogenic. That is, it's not formed from radioactive decay. It just exists. It is. So they used this feature. It's always good when you can change a problem into a feature. It's kind of like software companies do. To develop a radiometric dating technique called isochrone dating. So in the initial state, under our normal assumptions, we would have 4 lumps of parent, and they would decay like this, as we've already seen. But we might also have, as we talked about, some daughter element to start with. This is the excess argon that shouldn't be there, and it just stays there. And then in addition to that now, we've got this non-radiogenic element that also just stays there all the time. But we might not know what these are in different samples of rock. Let's say the same rock. Take different samples of it. They might have different values of that. So it might look like that, or it might look like that, or it might look like that, which is actually where we started. Now it turns out, if instead of measuring the ratio of the daughter to the parent, you measure 2 ratios, one which is the daughter to the non-radiogenic isotope, which in this case would be 7/4. Count the light green ones and the dark green ones. And if you also measure the ratio of the parent to the non-radiogenic, which would be in this case 1/4, and you plot those 2 ratios for different samples of rock, the same rock, that might have different mixes of the 3 isotopes in them, you get a straight line. And the slope of that straight line is the age. To show you how this worked, I created an artificial one. Ran a random number generator with some parameters in it to generate an isochrone. And so you see, you get this really nice straight line. I set it up so that it would be the equivalent of 3 half-lives, so the slope should be 7. And if you calculate the slope, it's actually 6.96. So this looks pretty good, right? And here's an isochrone, a real isochrone now, using the rubidium-strontium decay chain. And it's got a nice straight line. I mean, there's the errors on the points are a little bit more than the ones that I calculated, but still, looks pretty good. Here's another one. Using a different radiometric chain than I've talked about. It's a samarium to neodymium chain. And then here's a third one, which combines those 2 lead chains into a way that you can do a lead-lead isochrone. It all looks really good. Okay, so let's try this on our New Zealand volcano. Well, the rubidium-strontium isochrone gave an age of 133 million years. And the samarium-neodymium one gave one of almost 200 million years. That's like 3 million times the real age. And the lead-lead one I couldn't put on the same graph because it's 4 billion years, which is 80 million times the real age. Oh, and you know these 3 isochrones that look so really good? Well, you can see they all have different ages, right? And they're all very precisely known. Well, they're actually ages for the same rock. So what's the correct age? Who knows? Maybe none of these. Maybe the correct age is 6,000 years. After all, we've got 4 billion years for a 50-year-old rock. So we've got these 2 rocks. Top one is a basalt, and somebody tells you, based on radiometric dating, this rock is 3.9 billion years old. Bottom one's actually a meteorite, and somebody tells you, based on radiometric dating, this rock is 4.54 times 10 to the 9th plus or minus 1%. Sound familiar? And that is the age of the Earth. But you know that this rock is actually only 50 years old. So how do you know how old the meteorite is? Maybe its actual age is 6,000 years old, just like it says in the history book of the universe. Okay, so this didn't work very well. This didn't work very well. These didn't work very well. What about carbon-14? You may have heard somebody tell you carbon-14 proves that the Earth is millions of years old. Well, it actually doesn't. Carbon-14 is formed when high-energy cosmic rays collide with nitrogen atoms in the atmosphere, and they change them into carbon-14 atoms. Carbon-14 forms carbon dioxide just like carbon-12, well, more or less. And so it's carbon dioxide, and it gets absorbed by plants as part of the photosynthesis process. Animals eat the plants. We eat plants. We eat animals. So, folks, I'm sorry to tell you this, you're all radioactive. But fortunately, there's not very much carbon-14, so we don't glow in the dark. And when carbon-14 decays, it decays back to nitrogen-14. And of course, carbon also has a stable element called carbon-12. So when the plant or animal dies, it stops ingesting carbon-14, and the carbon-14 that's in its body starts to decay. And it decays just like the ones we've been talking about. So you start out with this amount of carbon-14 at time 0. After one half-life, half of it's changed to nitrogen-14. After another half-life, another half of it's changed to nitrogen-14, just like the other stuff. The half-life of carbon-14 is 5,730 years. So 2 half-lives would be twice that. Now, at the same time, in this dead body, there's all that carbon-12, and it doesn't change. So if you ignore the nitrogen-14, you can see that over time, the ratio of carbon-14 to carbon-12 in this dead body changes. And if you can measure that, then perhaps you can compute, just like we did before, how long this has been going on. Now, there's not very much carbon-14. There's 1 atom of carbon-14 for every 1.2 trillion atoms of carbon-12. Now, a trillion is probably a number that we haven't been very familiar with until just recently. But if you've been... Okay. But they have developed some instruments that can measure this. They're called accelerator mass spectrometers. They actually almost count the atoms. And you can determine the ratio of carbon-12 to carbon-14 down to 0.002%, that's 0.00002 of the amount of carbon-14 that is present in the atmosphere today. So they make all their references to what would be the normal starting point for the decay. And that sensitivity actually means that after about 15.6 half-lives, which is approximately 90,000 years, carbon-14 becomes undetectable even with these sensitive instruments. So carbon-14 cannot tell you the age of anything older than 90,000 years at most. Okay, coal. Coal is pretty much all carbon. And coal is found in pretty much all the geological layers, except that little one that's marked red. Don't know why it's missing out of that one. But some creation scientists took samples from some different layers. This layer, the Eocene, the Cretaceous, and the Pennsylvanian, which, according to the geological timescales, are 37 to 56 million years old, 71 to 145 million years old, 304 to 318 million years old. So these are all a whole lot older than 90,000 years. They collected them from different places around the U.S. Fortunately, they picked up some Pennsylvania ones from Pennsylvania. They sent them off to an AMS lab to be measured for carbon-14, and these are the results. Now, the sensitivity of the instrument is way down there. The average of all of these samples is 123 times the sensitivity. So it's not a measurement error. This is a big amount of carbon-14. The variation in the samples corresponds to carbon-14 ages of about 45,000 to 60,000 years. Now remember, the alleged geological age for these coal samples is in the millions of years, not the thousands of years, tens of thousands of years. Diamonds are another form of carbon. Very hard crystal, impermeable, hardest substance we know. And the creation scientists sent several diamonds away for carbon-14 dating, and here are the results. Again, the sensitivity of the instrument is way down at the bottom of the graph, almost can't draw it on the graph, and the average is 60 times the sensitivity. So again, it's not a measurement error, and that corresponds to almost the same age as the coal, even though the geological age for these diamonds is somewhere between 1 and 3 billion years old. Now, these radiocarbon ages for coal and diamonds are bigger than the 6,000 years that we got for the age of the Earth from the Bible. And why might that be? Well, there are a couple of reasons. One is that perhaps early on in the history of the Earth, there wasn't as much carbon-14 in the atmosphere. I mean, it might have started out at 0 and had to build up. And we know that the Earth's magnetic field is declining, so it was stronger in the past, so it would have been deflecting cosmic rays away from the Earth more, so it would have been formed more slowly and all of that. But probably the biggest reason is that there was more carbon in the biosphere before the flood. I mean, all that coal and oil and natural gas, that's all a result of decomposition of carbon material. And to see what effect that might have, here's the decay curve for carbon-14 as a function of the half-life along the bottom. If you take 50,000 years, is roughly the age of all these coal, diamonds, and stuff, that corresponds to a percent modern carbon of 0.236. Now, if you assume the coal and the diamonds were formed as part of the flood, the coal in particular, then that's about 45,000 years ago. So what if that was true, and the amount of carbon-14, the ratio of carbon-14 to carbon-12 at that time was the same as it is today, what should the measurement look like? It would be 58%. Now, that's a big difference. In fact, the ratio is about 1 to 245. So if this is the carbon-14 to carbon-12 ratio today, and this was the carbon-14 to carbon-12 ratio before the flood, because of all that other carbon, then if we use that as our assumed starting point, then the measurement would actually be 0.58, and the age of the coal would be 4,500 years. And all of this extra carbon would be the stuff that was buried by the flood. Now we need to talk about zircons. This is kind of turning into a geology class rather than a nuclear physics class. That's because there's so many chapters in the Bible about geology. Now, zircons are little wee tiny crystals, and apparently zircons love uranium. Or maybe it's uranium loves zircons, not too sure. But whenever zircon crystals form, they seem to have a preponderance of uranium in them. Now, uranium has a very complicated decay chain. Kind of goes on through a lot of stages. So uranium decays to thorium, which decays to lead-214, which decays to bismuth-210, which eventually decays to lead-206, which is the stable daughter. Now, you can see when it does that, it emits 8 alpha particles. And alpha particles have an affinity for electrons, and when they get 2 electrons, they turn into helium atoms. So what's going on inside these little zircon crystals, that every time a uranium-238 nucleus decays to lead-206, it produces 8 helium atoms. Now, helium is a very interesting chemical element. It is an inert gas, so it doesn't form compounds with anything, and it's also small, and it leaks through things, right? I mean, how many of you have bought a helium balloon? Maybe 3 days ahead of when you needed it, and then it looks like this. Because the helium leaks out through the balloon. Kind of looks like I feel in the morning sometimes. Well, this process is called diffusion. And really what it is where there's a high concentration of things, they like to spread out to where there are lower concentrations. And that's what would go on in the zircon crystal. It's kind of like, you know, if you're at a party and the room gets crowded, if there's another room with nobody in it, people tend to go into the other room, right? Well, you got this zircon crystal with all these helium atoms inside, and there aren't any helium atoms outside, so they all kind of want to wander outside. So what goes on in the helium crystal, or the zircon crystal, is a uranium atom will decay to lead and produce 8 helium nuclei, or helium atoms. And then they will start to migrate out of the zircon crystal. And then another uranium atom will decay to lead and produce some more helium. And this goes on and on and on. Now, some creation scientists got a bunch of zircon crystals from a very deep borehole that was drilled in the earth by the Los Alamos National Laboratory. And they looked inside these zircon crystals, and they found some uranium, and they found some lead. Based on the ratio, you know, that old calculation, how much daughter to how much parent, they calculated that the age of these zircon crystals, based on this ratio, was 1.5 billion years. Again, very precise. Now, if that, given the number of lead atoms that were in there, and the fact that each decay would produce 8 helium atoms, there would have been this many helium atoms produced. And given that the ages were actually 1.5 billion years old, you'd expect to see about this much helium. Maybe even less. It would have all leaked out. Long time, and helium's very slippery, so it would have all leaked out of the zircon crystals. In actual fact, this is how much they found. Up to 58% of the amount of the helium that was produced from that decay was still in the zircon crystal. So one of the scientists, Dr. Russell Humphreys, did a calculation, a model calculation, of what the rate of diffusion, it's called diffusivity, would be out of the zircon crystals for the helium if they were, in fact, 1.5 billion years old. And that's the number he got. He then did another calculation of what this number would be if the zircon crystals were only 6,000 years old. And this is what he got. And that's like 100,000 times different, which is not surprising because, you know, 1.5 billion is a whole lot bigger than 6,000. Okay, that was in the year 2000. In the year 2003, they managed to get some more zircon crystals from the same depths in the same borehole, and they sent them away through a third party to an independent lab to have this diffusivity measured. And here are the results. They agree exactly with the 6,000-year-old model. In fact, when he redid the calculations now for the best fit to the data, he got an age of 5,681 years, plus or minus 2,000. So, either the diffusion rates have been dramatically different in the past, or radioactive decay rates have been dramatically higher in the past. Now, these both seem like they shouldn't be, right? But one of them has to be. So is there a way we can pick one? To do that, we're going to look at things called radiohalos. When uranium decays, it emits all these alpha particles, right? And they fly off in all directions from the uranium nucleus, as indicated here. And when they do that, they run into the other atoms that are in the crystal structure. And they bump them out of their place in the crystal structure and produce faults in the crystal structure, dislocations. And you can see these dislocations when you examine the crystals under high microscopic power. And as they do this, the alpha particles, every time they bump somebody, they lose a little bit of energy. And this goes on like this until they get out to some particular radius that depends on how fast they started out. And then they lose a whole lot of energy and cause a whole lot of dislocations in the crystal, and then they stop. And so when you look at the crystal, you see this sort of thing. You see a dark disk in the middle where all the alpha particles are, and then you start to see these rings where the alpha particles with particular energy stop in the crystal. And the zircon crystal is a little wee tiny thing in the middle of it. This discoloration is in the crystal in which the zircon crystal is embedded. And this is a fully developed uranium-238 radiohalo, so it has 8 of these circles. But there are others. There's a polonium-210 radiohalo, and I'll show you this in a minute. The polonium-210 is one of the intermediate products in that decay, and it has a smaller number of rings. And in fact, polonium-210, which is the second last, has only a single radiohalo. And we can see that from here. Here's the full decay chain. So there are 8 alpha particles, and each one of them produces a little ring. For polonium-218, you only have these 3, which means, incidentally, that none of that other material is in that same place where you're getting the polonium-218. You only have the polonium-218 and later. And polonium-210 is right at the very end, and there is another one, polonium-214, which has 2 rings. So it's possible to calculate how many particles it would take to produce this kind of discoloration in the crystal, this kind of dislocation. It turns out it needs 100 million years worth of decay particles. That's at today's rate, right? If you use the half-life. Now, radiohalos are generally found in biotite, which is a crystal that is in granite that surrounds the zircon crystal. It's like mica. It's a form of mica, so it comes in all these sheets, that you can split apart. And they do that. They split them apart, and they look at them under high-power microscopes, and they count the number of radiohalos that you would see in a particular sample. And creation scientists took a number of samples of granitic rock from various places around the Grand Canyon Basin, counted all these radiohalos. Well, first they had to split apart all the flakes of biotite, and then they counted all the radiohalos, and got a distribution like this. And this is plotted as the number of radiohalos in a particular sample going up, and along the bottom is basically the rock layer, the geological rock layer, in which the sample was found. And they've plotted it using the standard geological time scale, so it's in millions of years. And these rocks would, in the geological classification, would be known as Precambrian rocks. These ones would be Paleozoic or Mesozoic, and these ones would be Tertiary. Now, in a biblical time scale, these would be pre-flood rocks, these would be flood rocks, and these would be post-flood rocks. Now, the flood was about a year long, so we now know which of those 2 possibilities to choose, because we now have independent evidence of 100 million years worth of decay in less than a year. So the radiohalos have supported the conclusion that about accelerated decay that came from the helium diffusion experiments. But they also tell us something more. Here's a radiohalo, here's a piece of biotite with both the uranium-238 halo and a polonium-214 halo. Now, if we look back at the uranium decay chain, that's what's in the uranium halo set, but in the polonium-214 halo, there are only these 2. So none of that other material is in that area where the polonium-210 halo was formed. And not only that, but between the 2, there's no alpha decay. There's no discoloration of the crystal structure. So no alpha decay happened in there. Might have been some beta decay, but no alpha decay. So how does this come about? Well, the biotite, as I mentioned, is a kind of mica, so it's got all of these thin layers with cleavage planes between them. And it's quite possible that hydrothermal fluid flow, that's a fancy term for hot water, dissolves some stuff out of the uranium source, transported it over to another defect in the crystal over here where it was deposited around something, and then it decayed and formed the polonium halo. Now, there's some other characteristics. This characteristic that there are no alpha particle tracks between there does 2 things. One, it means that all of that stuff that provided alpha particles in the uranium isn't part of the polonium, but it also places some limit on how long it took to move that material. To do that, we need to understand that we need to look at different phases of the rock as it was forming. And this is a hypothetical. I made this up. It doesn't bear any resemblance necessary to reality, but it's a reasonable representation of how the temperature might change in a rock over time. Okay? It gets hotter and hotter and hotter and melts, and then it cools off later on. Now, there are two temperatures that are important here. One is the annealing temperature, because when the rock is above the annealing temperature, there's enough energy going into the rock that it repairs all of those dislocations that happen when the alpha particles come out. So the alpha particles come out, bump into something, knock it out of a place, and there's enough heat in the rock that the heat pushes it back into its proper place. So you only get tracks when the temperature of the rock is below the annealing temperature. You don't get any tracks when the temperature is above the annealing temperature. And then there's another temperature at which the water that's in the rock gets released and available for hydrothermal flow. So the only time we could have that transport between the uranium site and the polonium site happen was when you are between those two temperatures. But the other thing you have to consider is, if that takes a long time, then the material that formed the polonium radiohalo would decay on the way. So if it's taking like millions of years to flow across, all the polonium will decay, and you won't get a polonium halo. So it's reasonable to assume that flow would have to happen in about 10 half-lives. After 10 half-lives, you're down to 1/1000th of the material you started with. So there would likely be not enough to build up the radiohalo over time. So if we say that time is less than 10 half-lives, and then we go back and look at the decay chain, particularly for the polonium halo. Remember, we have those two alpha particles, but we don't have any of the other ones. And we look at, so we're kind of down in the bottom, the second bottom row decay. We look at the half-lives. The lead decays to bismuth in 27 minutes. The bismuth decays to polonium in 20 minutes. And the polonium decays to lead in 160 microseconds. So it's probably not the polonium that's going across, but it might be the lead or the bismuth. But that means that flow happened in a few hours. So the rock was in that proper state, so you don't get any alpha tracks, for only a few hours, not millions of years forming it. So radiohalos indicate rapid rock formation, like hours, days, weeks, not millions of years. And the uranium halos in the same rock indicate their formation in the same time frame. So this once again confirms the accelerated nuclear decay that first came to light with the helium diffusion. Now, there are some issues with this. What caused the accelerated decay? And when, and I'm looking at the wrong slide. And when that happens, when decay happens, there's a lot of heat produced, right? That's what goes on in fission reactors, and you get a lot of heat produced. So how is this extra heat removed? Now, there aren't definitive answers to either of these questions, but there are some ideas kicking around. For example, the rate at which alpha particles come out of the nucleus depends on the shape of a thing called the nuclear potential well, which again itself depends on the strength of the nuclear force, the strong nuclear force which acts between neutrons and protons to hold the whole nucleus together. And calculations indicate that a relatively small change in the nuclear force would change the potential well in a relatively small way, but a big enough way to make a big change to alpha decay, particularly alpha decay with a very long half-life. Doesn't affect so much things with a short half-life, but with a very long half-life, they would make a big change. Now, some people might say, well, if you were telling somebody this, they would say, well, yeah, but, you're taking exception to the kind of the laws of physics and all of that. Well, doesn't this happen in evolution? What caused the Big Bang? Dr. Faulkner talked a little bit about the Big Bang last night. It goes from nothing to everything. So it violates the law of conservation of energy. What causes the baryon asymmetry we see? This is, baryons are the heavy particles like neutrons and protons, and that's what everything we see is made of, right? It's made of what we call matter. But since there was nothing to start with, there should be an equal amount of antimatter formed, so they sum to zero, but we don't see any antimatter. And the only way you can get rid of antimatter is to have it combine with matter, and then they both go away. So how come we see all these baryons? Well, there was a baryon asymmetric process early on in the Big Bang. Okay? It also violates the law of conservation of mass and energy. And then there's the how-to questions. How did life form from non-life? Nobody knows the answer to that either. And it violates the first law of biology. And evolutionists just ignore it. Or as talking about the incredible amounts of information in the genome that Dr. Carter was talking about, one of the evolutionists has said, how did stupid atoms spontaneously write their own software? No one knows. So the fact that there are a couple of issues with the creationist view of radiometric dating shouldn't be taken as, throwing the baby out with the bathwater. So what have we learned from nuclear physics? We've learned that radiometric dating is untrustworthy, right? Mount St. Helens, lava dome showed us that. New Zealand volcano confirmed that it was untrustworthy, even the isochrones, which were supposed to fix the problem. Isochrone untrustworthiness was confirmed by samples out of the Grand Canyon Basin. And it's all because of these unknowable assumptions that are behind the calculation. Coal isn't millions of years old, nor are diamonds. In fact, it would appear diamonds and coal are about the same age. Zircons show us that the age of the Earth is indeed 6,000 years and point to a period of accelerated nuclear decay, which radiohalos have confirmed. Most of all, we've learned that nuclear physics is not a hazard to the Word of God. Now, if I've whetted your appetite for more nuclear physics, I highly recommend these two books. These two books contain all of the, the first book, the volume 1, Radioisotopes and the Age of the Earth. So it was a group of creation scientists who got together. It was called the RAPE Project, who did most of the work that I've reported here. And the first volume sort of is at the start of their exercise, discusses the state of the science, where they were and what they were going to do, and volume 2 records all of their results. Excellent books. A bit technical, but excellent books. The downside is there's only one copy of each on the table. So be careful as you stampede out to get them. But as Richard said, they'll order some in for you. If you prefer a Reader's Digest condensed version, these are also excellent resources. Thousands, Not Billions is a summary of volume 2 of that work, and it comes in either a book form or a DVD form. If you like to read it to put yourself to sleep at night, the book form is the one to go. And then there's one, The Mythology of Modern Dating Methods, which is written by John Woodmore, who he looks at all the different issues that people raise with respect to the creationist interpretation and deals with them and dismisses them. But even if you don't buy the books, remember this. Thank you very much. We got any questions? Yes, right here. Yes, percent modern carbon. Correct. That's in the atmosphere, correct. because there are a lot of carbon-12 atoms. And the percent is the percent of modern carbon. So they measure the ratio, 1 to 1.2 trillion, and they measure that. Because they've got, when you take a lump of coal, you've got lots of carbon-12 atoms, so you've got lots of carbon-14 atoms, and so they're able to measure that. Oh, I should have repeated the question. I'm sorry. Oh, my goodness. Way back there. Sorry, say again?
Does sample exposure to water affect radiocarbon dating?
Sample exposure to water.
If the material you're measuring was in water at some point of the decay process, for want of a better term, does that affect radiocarbon dating?
Well, the presence of the water won't, how does having a sample in water affect radiocarbon dating? The water won't affect, excuse me, the decay process, okay? And the water itself wouldn't introduce any contamination into the sample itself. This water is hydrogen and oxygen, no carbon in it. If there was other carbon in the water, that could be an issue. But when the labs that do these measurements are very careful. They've grown up, if you like. They're very sensitive to the potential for contamination getting into the product, the sample. So they take a great deal of care in the process, and they've refined their process over time, so the potential for contamination is essentially zero. Yes, right behind that. Well, they generally, the question was, what counter-arguments do evolutionists come up with when they see the radiocarbon dates for coal and diamonds? Typically, what they say is it's due to contamination. Although, as I've indicated, it's not any contamination that's introduced during the process of measurement, because the labs are very good at that. So they make arguments like, well, it's in situ contamination, that the coal was actually contaminated while it was still in the ground. But none of this holds water at all. Sorry for using water again. None of this holds up because, how does carbon-14 get from the atmosphere all through these rocks in order to get into the coal to contaminate it? Other people have suggested that the in situ contamination was caused by neutron absorption of the coal from radioactive decay in the rocks around it, but there's just not enough uranium in the rocks around it to produce enough thermal neutrons to do it. So they're grasping at straws. Now, there was another one over here, yes.
You said that the theory for calculating these dates down, that there are these assumptions that change.
Yes.
But aren't there also assumptions in figuring out these half-lives, particularly long half-lives, given billions of years, no one was there. So what are the assumptions in calculating what these half-lives are?
Okay, the question was, since there are assumptions in doing the calculations to determine age from radiometric dating, are there any assumptions in determining the half-lives of the materials? And if so, what are they? Well, actually, the half-lives are all measured. So there are, I think it's fair to say, there are no assumptions in determining the half-lives. And what you do is you set up an experiment with an amount of radioactive material, and you count the number of decays. They have detectors that will detect alpha particles, and so you count the number of alpha particles that are given off by this material for a small period of time, and then for the next small period of time and the next small period of time. And you do this over a longish period of time, kind of as long as you're prepared to stand around and look at it, and you plot those numbers on a piece of semi-log graph paper, or if regular graph paper it would look like that, but on a semi-log paper it's a straight line, and the slope of the straight line is the half-life. And for the billions of years one, it just takes a lot of material and a longish time to do that. But you can get, you're working up in an area where if you extrapolate, there'll be a larger error, a larger precision, uncertainty, than for some of the smaller half-lives, but they're still very accurately measured. So there really aren't any assumptions in measuring today's half-life. The assumption is that that half-life has always been the same, which some of the evidence suggests is not the case. Yes?
So there are no reasonable contaminations that you can think of that would go while the rock is still around. That's why you need to conclude that the change in half-life is that explanation for seeing that we've seen.
Yeah, yes, and there are a number of lines of evidence that support that conclusion. It's not like one measurement, but we have several lines of evidence now that support that particular conclusion. Yes?
Heard over the last couple of years that Stanford scientists found out that the decay rate is not constant. Have you done any research in that area?
I personally haven't, but yes, I have read things that. Oh, sorry. The observation was that there have been experiments done that indicate that the half-life it isn't constant. As I say, I haven't done any of those myself, but I am aware that some experiments have done that. Some of the one of them, for example, showed that if you could strip all the electrons away from a particular nucleus, the alpha decay rate went up by 9 orders of magnitude or something like that. But getting rid of all of the electrons requires an input of a huge amount of energy, and so that would not be a way of accounting for the increase in the half-life. But yes, or not the decrease in the half-life. But yes, there is some evidence that the suggestions that are being put forward for how this might happen are fairly reasonable. Yes?
You talked about the response of say, the old Earth proponents to the radioactive dating, the coal and the diamond. But what about the response to the other method, like the rocks from the volcanoes? The response of the older.
Yeah. So I think if I.
You mentioned with the radiocarbon that they say is a contamination problem. What are they saying in reference to the other dating methods for the older time periods?
Pretty much this. Oh, sorry. The question was if the response to the radiocarbon dates are that it's contamination in the material, what are the responses to the dating of the rocks? Pretty much the same. I mean, the potassium to argon dating method is pretty well recognized now to being not very reliable. They still use it because it's easy to do, but it's there's an interesting thing when you send samples away to be radiometrically dated. You send it with a form to the lab, and one of the questions they ask you is, how old do you think this is? So what they do is mess about until they get an answer that's more or less what you thought you were going to get. And there's one, I don't remember what his discipline was, but he was quoted as saying, if we get a result, a radiometric date that agrees with what we want, we'll put it in the article. If we get one that's close, but not exactly what we want, we'll put it in a footnote. And if we get one that doesn't agree at all, we just forget about it. Any other questions? Do we have any time for any other questions? Yes.
Do you believe that all our coal and oil reserves form during the year of Noah's flood or shortly after? Because to synthesize it, we know only takes about 38 years.
Yeah. So I think it's perfectly reasonable to assume that. Yep. Yes.
The evolutionary scientists say, since the discovery of carbon 14 and diamonds, what's that answer to that? Diamonds are pretty attribute.
Yeah, the question was, what do the evolutionists say about carbon in diamonds? Because diamonds are pretty impervious, and that's absolutely right. I'm trying to remember. Jonathan Sarfati wrote an article on that, and I was trying to remember what he said. It's on the website under diamonds, and I can't remember. I think they just kind of ignore it. Any more? Okay. I'm sorry. I'm getting the signal.
Probably one of the best presentations that I have ever heard in a long time on nuclear physics and radiometric dating. That is Dr. Jim Mason. Of course, all of these sessions will be available in the archive list on the front page. I just uploaded that page about 5 minutes ago. And it's taking us some time because we are in a location where the internet is very sketchy. So it's taking us some time to get the sessions uploaded to the page. But I want you to know that we're working on it. Rich is already on the page. On the bottom of the front page, if you go to BibleDiscoveryTV.com, you will see our sessions here. That's where you're going to find it. So if you happen to be watching and you're up very late in Australia, some other part of the world, keep an eye on that archive sessions here, and that will take you to links that we have been able to post. Now, today I hope to get 3 more sessions up. But again, it just simply depends on how we're doing with the internet. We're going to continue broadcasting with our live here of Creation 2011 Super Conference. There's lots going on at Muskoka Bible Center. Kids creation are going on with snakes right now. It's being maybe we'll show you of that and archive it on our YouTube channel. I think find some interest. Also, a moment about Dr. John Sanford. And Dr. Sanford is an amazing man. We had an amazing interview yesterday. He is going to talk about how evolution through science and how the Bible actually is consistent with science. That's coming up at about 10:30. From now until 10:30, we're going to run some music with some slides showing you what else is coming on in the day. We'll take a break in the afternoon, and we'll come back tonight at 7 o'clock with Dr. Robert Carter. Is going to be presenting some fascinating evidence on the Genesis flood related to the coral reefs. Now, this is some amazing material I have ever heard. And also, a little bit later on, my good friend, who I enjoy and love dearly, Gary Bates, is going to come along. He just updated his new book called Alien Intrusion. And he's added an entirely new chapter. He was talking to me about it yesterday. And, of course, there will be question and answer as well going on with that. So there's lots to come today, and it's going to be very good. Now, again, I want to mention that if you've just tuned in to coverage of the live 2011 Creation Super Conference, that you can see the recorded sessions earlier this week. Lord willing, later this day, we'll get a few more sessions up at archive sessions at the bottom of the front page of BibleDiscoveryTV.com. BibleDiscoveryTV.com. That's where you will find it. Now, I'm going to try to send those links to the Creation Ministry, CMI, so they can send it out in an email as well. But just have a little bit more patience with us, and we'll get that sorted out. Again, we're in a situation where internet is not exactly forthcoming out here in the beautiful, beautiful southern Ontario weather. It's gorgeous out here. I'm Rod Hembry. This is live coverage of 2011 Super Conference on Bible Discovery TV and Radio211.com. Now, we're going to come back in just a few minutes. We've got about 15 minutes, maybe a little bit less, before we'll come back and do some highlights of what we're going to see with Dr. John Sanford, evolution and how evolution actually damages the credibility of science and how the Bible is compatible with the credibility of science. That's coming up in less than 20 minutes. So you'll want to make sure that you get a hold of that. In the meantime, we'll go to our slides now with some music. Stay there as live coverage continues from Muskoka Bible Center. I'm Rod Hembry with BibleDiscoveryTV.com.